Okay, we got something a little different here. We got a homemade integral and we're using the blackboard, the digital blackboard. I'm going to experiment with using the blackboard and the whiteboard going back and forth. So we have this integral. We got the integral from minus pi over 4 to pi over 4 secant squared x 1 plus pi to the x cubed dx. Okay, I want to blame someone else for this, but I'm the one that did this problem, so I stuck that pi there. Anyway, I was thinking this looks pretty tricky, but the thing we have going for us is we have this symmetry in our bounds, right? This is symmetric around the y-axis. So we can use that, and what we usually want to do, kind of like King's principle, we can try to do a U-substitution where we add the bounds together, pi over 4 plus minus pi over 4, 0, and we just do a substitution, u equals minus x. Then we can just solve for our x value as minus u. So dx is going to be minus du. Let's do our substitution. So when we do this, so the balance is real simple. We're just going to change the sign, right? So this is going to become a minus pi over 4, and this is going to become pi over 4. Okay, so in the numerator, we're going to have secant squared, then we're going to have a minus u over 1 plus pi. That x is going to become minus u. So minus u all cubed, but the minus sign is just going to come out. So I was going to put parentheses around it, but it's the same thing. So we're just going to have that minus sign there. And then our dx is going to be minus du. And what I'm going to do right off the bat is I'm going to use this minus sign to change the balance. We're going to flip it, but in this case, it's pretty easy to flip. So it's just going to go back to what it was. And a couple other things with the sign. So like, okay, here we have a minus u inside a secant squared. Well, secant is just an even function because cosine's an even function. So this minus doesn't do anything. We're just going to get rid of that minus sign right there. And so you notice with these kind of problems, we're trying to kind of get it similar to what we have in the denominator because we want to like add these things together. So like we'd like this to be exactly the same, different variable name, but we'll deal with that in a minute. So the real problem, the issue we have here is this minus sign. Well, I can fix that, and let's see how that's going to go. So what I'm going to do, we'll multiply it by pi u cubed over pi u cubed. Okay, and let's see what happens when we do that. So let's get a little more space. Okay, so multiplying this out, we're going to still have our secant in the numerator. Then we're going to have it times pi u cubed. Such a weird expression, pi u cubed. It's like I can't think of ever seeing that ever. And I just made that up. So that's how creative I am. But anyway, moving on, we'll multiply this in here. So multiplying pi u cubed times minus pi u cubed, well, we adding the exponents, we get 0 in the exponent, and that's just going to create pi to the 0, which is 1. So we'll write down our 1. Then we're going to have 1 times pi u cubed, and we just have pi u cubed. And then for my next step, what I want to do, what we can do here is we can do a variable change. And that's, again, like I was saying, we're going to want to add this back to our original integral. And the original integral was in x. So let's just change this all back to x. I'm just going to rewrite it and change my variable. I can do that, but it's a definite integral, right? Because the definite integral is the area under this curve. And the area under the curve does not change regardless of the variable name. So let's do a quick rewrite while you guys aren't looking. Okay, from here we have it set up. And what we're going to do, let's kind of zoom here. So we have this integral. And what I want to do, so I really changed the size on this thing, but anyway, our original integral we're going to call I, okay, and we're going to also call this integral I. And we're going to just add them together. We notice we got the same bounds on here, okay, the pi over 4. We've got the same variable name. We got the same denominator. So we're set up to add these up nicely. So let's just do that and see what it looks like. You know, we've added these together, and we have a few things to notice, right? So we added them together. Now we got 2 copies of the integral. So therefore, we got 2i over here. And then I did kind of skip a step, right? Because there could be a step where we have this as 2 integrals. Okay, but I actually combine this into 1 integral because we have, like I said, the same variable, the same denominator. So I just put it all under 1 integral sign. We had the secant squared from the first one, and then we had this from the second one. And then from here, what I can do to take another step is let's just factor out, we can factor out this secant squared that we have in common. We're going to have up top in the numerator, we're going to have this 1 minus pi x cubed. And that's nice because that's exactly what we have here in the denominator, okay? Which gives us this cancellation that we want, which leaves us integrating secant squared. And the beauty of that, of course, is that we know what that is. That integral is the integral of secant squared is just tangent of x. So we just have to evaluate tangent from pi over 4 to minus pi over 4. I could have used the even function over here, but I forgot. So let's not worry about it too much. Let's not lose any sleep over that. So what I'm going to do, let's bring this up. So let's just evaluate our tangent. Okay, so tangent at pi over 4 is 1 minus tangent at minus pi over 4 is minus 1. Well, minus minus is plus, and then we just have 2. But 2 is not quite our answer because we have 2 copies of the integral 2i, so we just divide this by 2. And so our solution to this whole thing is going to be just very nicely 1. That's it. Thanks, everyone. Have a great day.